a rational function is just, it looks like this. R of x equals f of x over g of x, where f of x and g of x are polynomials, and g of x is not 0. Okay? It's called a rational function. Now, the domain of this is going to be all real numbers except for the zeros of the denominator. Okay? So you know that. We've done domain a lot, right? So we're going to, number 1, graph on our calculator and find the domain of these functions. So you could do the domain without graphing, but I just want to show you what these look like on your calculator before we graph them. And we're going to graph most of these by hand, but I just want to show you what they kind of look like. They all come from a parent function. Let me show you what the parent function looks like. The book talks about shifting and reflecting and doing a bunch of stuff. I don't teach it that way. Mrs. Pfeiffer does, and it works out well, and she really likes it. I don't know. I just don't like it that way. But the parent function is this. It's just f of x equals 1 over x, and you have that, and you have this. Okay? And so it's not a continuous function. It has a break in it. The domain of this would be all reals except for 0. And so they're all going to look something like this, though, for the most part. Okay, so did you graph it on your calculator and you found out what it looks like? Yeah? No. Okay, so let's do that. Here we go. Go 3 divided by, make sure you put parentheses, x minus 1. Hit zoom 6. And there you go.
How come it's different if you don't put parentheses?
Because what it's doing, if you don't put parentheses, it's doing 3 divided by x and then minus 1. Yeah. So there you go. And that's what it looks like. Okay? So graph it on your calculator. So let's go ahead and draw a little sketch of the graph. It looks like there's a problem at 1, right? So the domain is going to be all reals except for when x equals 1. And at 1, there's an asymptote there. And then we're also going to learn that there's an asymptote at 0 here. Okay? And that's where the limits are going to come into play a little bit. So here's our graph here, and there it is there. And it's just like a sketch of it. Okay? So if you go to the table with me, go to your table, which is second graph. And, oh, by the way, did you know that if you ever get stuck like somewhere far away and you want to get back, you can go to table set, second table set, and you can start your table at any number you want to. So let's say I'll just start it at 0, okay? So there you go, the table set. So if I go ahead and I'm following my x's all the way out to infinity, I'm going super far. Do you see what y is doing? It's going 0.10, 0.1, 0.09. What is that approaching? What is that getting closer to? Yeah, it's getting closer to 0. So what they do is they say the limit as x goes out to infinity for this function is equal to 0. Yeah?
Mine just says 0.
It does? It actually just says 0, way out there. How far out there? Or is that for y2?
Y2. Or is it supposed to say? Oh, we're looking at y1.
Y1, yeah,
oh,
yeah.
Okay.
Y2, you have 0 there.
Okay.
Yeah, because we usually have 0 there. All right, so there you go. And then also, if you go the other direction out towards negative infinity, the limit as x goes to negative infinity for this function is also equal to 0. And so if you do it this way and you go, okay, I'm going to follow this graph out towards negative infinity, which is way to the left, my line, my graph is getting closer and closer to y equals 0, the line y equals 0. Okay? All right, let's do the next one. First of all, what's the domain of this? All reals except?
1 and negative.
Perfect. Plus and minus 1. Okay, it's what makes it 0 in the denominator. So what would make x squared minus 1 equal to 0? Well, you can set it equal to 0 and solve. Add 1. Take the plus and minus square root. So you get plus or minus 1. Okay? So if I plug in 1, that's not going to work. I'm going to get 5 over 0. And if I plug in negative 1, I get negative 5 over 0. Very bad. So let's go ahead and graph these now. Don't forget parentheses. So 5x divided by x squared minus 1. We're going to end up graphing all of these types of things by hand too. So here it is. This one's kind of interesting. There it is. All right, what happens is there's kind of three parts to this graph. And because x can't be plus or minus 1, what happens is there are two asymptotes to this graph, two vertical asymptotes. So one looks like that, the other one looks like that, and our graph's not going to touch that at all. You can never, ever touch vertical asymptotes, okay? Because x can't be 1 and it can't be negative 1 in this function. And so over here, I have it's going like that kind of a branch. Over here, it has this kind of a branch. And then in the middle, it's going to act like one of two things usually. It either acts like a cubic function or a parabola. So in this case, it acted like a cubic function through here. There you go. Okay. And so what they say about limits, they talk about limits as you go out to infinity, but then they also talk about limits like what happens when I have x going to 1 plus and x going to 1 minus. Okay? Yeah.
Can you go to your Whiteboard?
This right here? Parentheses. Did you put parentheses? Oh.
It does something weird.
Try again. Okay, so as I'm going to 1 plus, that means that I want to look at what's happening on the right side of 1. You got it? Good. And then 1 minus, I want to look on the left side of 1. Okay? So let me show you what that means. So here's 1, x equals 1. This is the right side, and this is the left side. So let's jump on our graph real quick. And let's go towards negative 1, or positive 1, from the right-hand side. Where are my y's going? To infinity. You see that? The closer I get to 1 on this graph, right? I'm getting closer and closer to 1. My y's are getting very big. So that would be infinity right there. And look on the other side. Let's look on the other side now. As I'm going towards 1, still 1 right here on the left side, this is the left side of 1, and I'm going this way, what are my y's getting closer and closer to? Negative infinity. Okay. So when that happens, that's when you get vertical asymptotes. Okay. Now, I'm not going to be too much on limits because limits show up at the very end of the year. It's very calculus, and that's what we do then. But the book introduces you to limits right now just a little bit. Okay. So don't be scared. I'm not going to ask you a bunch of limit questions. Okay, so now let's go ahead. We're going to talk about asymptotes, holes, and zeros of the graph. All right, so we're going to have vertical asymptotes. The vertical asymptotes are going to be the zeros of the denominator except when they're not. Yeah, there's something that happens where it turns out that it's not a vertical asymptote. Okay, I'm going to show you what that means. So zeros of the denominator unless it's a hole in the graph. And I'll show you an example of each right now. Okay. So let me just show you. If you have f of x equals 3 over x plus 2. Okay. 3 over x plus 2. And if you were to graph this thing, you would see that there is an asymptote, zeros of the denominator, so x equals negative 2 would be a vertical asymptote of that graph, okay? We saw it up here, positive 1, negative 1, they were both asymptotes. Over here, positive 1 was an asymptote. X equals negative 2 would be an asymptote. Now what happens is not all zeros of the denominator are going to be asymptotes, so let me show you the exception. If I had f of x equals x squared minus 4 over x plus 2. Okay. You look at this and you go, oh, okay, it's the same type of thing. You know, I had a vertical asymptote of negative 2 because that made it 0. But what happens is when I factor this, x plus 2, x minus 2, you get the same factor in the numerator and the denominator. And so what that does is that will make it so that you have a hole in the graph instead. Okay? So that's the only exception. Otherwise, it'll be an asymptote. Okay? Unless it has the same factor, because what you do is you can reduce it out. And then when you graph that, it's a line with a hole in the middle. A hole in it. I'll show you. So you go to your calculator, and you graph this thing, x squared minus 4 divided by x plus 2. And then I graph this, and it looks like a line. And you're like, what? How is that a line? Okay? But if you look carefully, you know, what is the domain of this? All reals except for -2. If you hit trace and you plug in -2, guess what? Do you see that? There's no y value. Or yeah, you go to your table. Dang it, my table's way out there again. You go to your table and you go to -2 and there's an error there. Okay? Errors will show up as asymptotes, but they'll also show up as holes in the graph. But if you look at your graph, you will see that there's no asymptote there. It was a line, right? It looked like that. But there's a hole in the graph right there. Crazy. So that the only time that happens is if you have the same factor up top that you do on the bottom. Okay? It's called a removable discontinuity. All right, let me get rid of that right there. Okay, so that's holes and that's vertical asymptotes. Now let's talk about horizontal asymptotes. Okay? Horizontal asymptotes, sometimes they don't affect all of the graph. Okay? You can actually go through a horizontal asymptote. This graph right here has a horizontal asymptote at y equals 0. But look what happens in the middle. What? My graph went through it. You're not allowed to do that. Sure you are. Horizontal asymptotes for these, they only affect the outside parts. Okay? So you can go through a horizontal asymptote just fine. So there are 3 different ways to find a horizontal asymptote, or 3 different types of horizontal asymptotes. Okay? So here we go. We're going to go through them. Number 1. If the degree of the denominator, okay, I'll call it d of x, is greater than the degree of the numerator. We'll call it n of x. Okay? So let's say we have some function n of x over d of x. So if the degree, if the polynomial in the denominator on the bottom is bigger, it's a bigger degree polynomial on the top, then you will get a horizontal asymptote of y equals 0. Okay? Every time. Every time. It's the reason why is because when you plug in x is infinity, because that's what you're looking at, infinity, then the bottom's going to get super big. And what's like 1 over 1,000, 1 over 10,000, 1 over a million? It's getting closer and closer to 0. Okay, the second one. Are you running out of room here? I am. If the degree of the numerator or denominator is less than the numerator degree, okay? Then you will have no horizontal asymptote at all. Because x is getting bigger and bigger and bigger, and it's going to infinity, so will your graph. It'll go off to infinity with no asymptote. And then finally, the third one. The third one is, what am I missing here? So I got bigger, less than, greater than, how about equal to? The degree of d of x equals. Not that the functions are equal, but that their degree, okay? Degree. If the degrees are equal, then the horizontal asymptote will be the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay? That's everyone's favorite. That's the easiest one.
Leading coefficient of the denominator?
Of the numerator over the leading coefficient of the denominator, yeah. So you take the leading coefficient of the top, leading coefficient of the bottom. Everything else just kind of cancels out. You just ignore it. All right, so here we go. Let's practice. Let's find all the asymptotes and holes and zeros and all this fun stuff, okay? Without graphing on our calculator. So here we go. The first one, very basic, okay? This one is, it has no holes in it, okay? Super easy, basic problem. So let's go ahead and first find the vertical asymptote. Vertical asymptote are going to be the holes of the denominator, or I'm sorry, the zeros of the denominator as long as they're not holes in the graph. And so that would be x equals -3. Okay. Vertical asymptote. Horizontal asymptote, you have to look at your 3 cases. Okay? Let's talk about the degrees here. The degree of the numerator is smaller than the degree of the denominator. The degree of the numerator is 0. The degree of the denominator is 1. So the denominator kind of wins. Like if I was going to plug in infinity, I'd get 5 over infinity, right? That's like 0. So the horizontal asymptote is y equals 0. And then it also wants you to find the zeros, okay? The zeros of this are found when you let f of x equal 0. So this is when f of x equals 0, and then you have to solve it. So if I plug in 0 over here, can I ever get this fraction to equal 0? No. 5 over something is never going to equal 0, okay? If you don't believe me, then you can cross multiply. When you cross multiply, you get 0 equals 5. Does 0 equal 5? No. So there's no zeros, and there's no holes in the graph. So there you go. Vertical asymptote, horizontal asymptote, zeros, none. The zeros are the x-intercepts, okay, that we learned. We did those when we were doing our polynomials. Okay, let's look over here at letter B now. Can you factor the denominator? We're only doing real numbers. So, nope, can't factor the denominator. Okay? And so there's no problem with this one. The domain of this one is all real numbers. Right? I can plug anything I want to in for x, and there's never going to be a problem. So there's no vertical asymptotes. There's no holes in the graph. It's a continuous function. So vertical asymptotes, I would say none. Holes, I would say none. Now let's look at the horizontal asymptote. Okay, so once again, compare the degrees. What I do is I look at this and this. And I don't know about you, but I'm not very good at memorizing stuff. So sometimes if I forget my 3 cases, I'll just look at the leading coefficients of the numerator and denominator, and then what this does is it's negative 2 over x. And then I think about, what if I'm going out to infinity? What is that going to be? 0, right? I'm getting negative 2 over infinity. That's a very small number. So the horizontal asymptote would be y equals 0. If you are good at memorizing your 3 cases, then great. Just remember that if the denominator is bigger, it's going to be y equals 0. Okay, now let's find the zeros of this thing. The zeros would be to plug 0 in for f of x and solve. And when you do that, you really don't need to worry about the denominator. Because if I have a fraction, and I want my fraction to equal 0, then I want the numerator to be 0, right? 0 over 8, 0 over 20, 0 over who cares? So if you cross multiply, it's gone anyways. And so you get 0 equals negative 2x plus 1. Subtract 1 to the other side. Divide by negative 2. So x equals 1/2 is a 0. That means that would be an x-intercept on your graph. Okay? So it's asking for all those things. Alrighty. 2 more. Then we'll take a little break, little head break. Okay. So for this one, first of all, the domain is all real numbers except for negative 5. Negative 5, no good. Okay? Now, you think maybe, negative 5 is a vertical asymptote, but it's not. Be careful. You need to factor. When you factor the numerator, you get x plus 5 and x minus 5. And so what happens is it's going to be a hole in the graph. Okay? Because you remove it. It's like you just take it out. It's just a hole in the graph. So x equals negative 5 is a hole in the graph. Vertical asymptotes would be none. Vertical asymptotes are only the zeros of the denominator that are not holes in the graph. This one, this negative 5, happened to be a hole. And then the horizontal asymptote, here, the top degree is bigger than the bottom degree. Okay? So if you think about it, and you're plugging in x is infinity, is that an asymptote? No, it's going off to infinity. Okay, so the horizontal asymptote would also be none. And we graphed this a minute ago. Remember, it looked like a line with a hole in it? So it looked like something like this. Well, not through 0, but it has a hole in it. And as I'm going out towards infinity, what's my y value is going to? Infinity. So there's no asymptote there. Does that look like it has an asymptote? No. Okay, last one. You want to try this one? Not yet.
What do you do for the zeros from the left.
Oh, zeros. Yeah, yeah. Good call. The zeros, this one would be tough a little bit. The zeros would be after, well, no. Just set it equal to 0 and solve. If you set it equal to 0 and solve, the only thing is, be careful, because when you solve this, you get x equals plus or minus 5. But you know that negative 5 is not a 0. Negative 5 is a hole in the graph. Okay, so it kind of tricks you into thinking that there's 2 zeros, but there's only 1 0. The 0 here would be x is 5. So I didn't really graph this very good. It should be like more like that. X is 5. Okay, so that'd be a 0. Sometimes it's good to find zeros after you reduce when you find the hole, and just set that equal to 0 and solve. Okay, thank you for reminding me on that. All right, letter D, last one. Okay, so we know that there is a problem at plus or minus 1. Now, the question is, are they both asymptotes? Okay, so we have to figure out if they're asymptotes or if they're holes in the graph. And so what we do is we need to factor. Factor the numerator. And the denominator. So what times what's negative 3 adds up to 2? Positive 3 and negative 1. And then the bottom factors is x plus 1, x minus 1. Okay, so let's talk about all the stuff, okay? So my vertical asymptote, there's only going to be one because this one ends up being a hole in the graph, the x minus 1 and the x minus 1. And so I have a vertical asymptote at x equals negative 1. That comes from this right here. There's a vertical asymptote at negative 1. There is a hole in the graph at x equals positive 1. Okay. There is a horizontal asymptote. My horizontal asymptote, ooh, finally, we got to one of these. All the other ones have been greater than or less than. This one is equal to. So this is what you do. You take the leading coefficient over the leading coefficient. Okay? So it's kind of like this. You take x squared over x squared. What does that equal? It equals 1. So our horizontal asymptote is 1. Okay? If I had something like 2x squared plus 3 over 5x squared minus 1, what you do is you take that, and the asymptote would be 2/5. Okay? All right. And then the zeros. Set this equal to 0 right here. You don't want this to be a 0. It's a hole in the graph. So x plus 3 would equal 0. So the 0 would be at negative 3. That would be our 0.
Do anything with the bottom?
No, because fractions, you want the top to be 0 in order for it to be 0. Let's graph this thing, and I want to show you exactly what it looks like on the calculator. And then we're going to spend a bunch of time graphing all these things by hand. But now that we know how to find the parts, I think that you'll be okay. By the way, if you're going to graph this, don't ever graph it after you've reduced it, because it's not going to be the right graph. Okay, graph the very original graph right here. That's the graph we need. So let me show you what it looks like. Here we go. Okay, so you can tell, look at it. You can tell that there is a vertical asymptote over here. Do you see how this is going down to negative infinity, that's going up to positive infinity? There's an asymptote at x equals negative 1. We found that, right? If I hit trace and I plug in negative 1, there's no y value there at all. Now, let's look at x equals positive 1. No y value. There's a hole in the graph, okay? And then, what was our 0? Was it negative 3? Yeah, our 0 is at negative 3. Okay? So we found all the pieces. I graphed it on the calculator, and now the next part of the lesson is going to be graphing all of these without our calculator. All right, so move on to the next page. We have 5 examples. Let's try and get through them. Let's go. Okay, graphing by hand. Here we go. Consider the function f of x equals 3 over x minus 2. We're going to find the following. Okay, I gave you a very basic one to start off with. So first of all, we need to find all these things, and then we'll graph, okay? So what is the vertical asymptote? Who can tell me what the vertical asymptote is?
X equals 2.
Perfect. And don't just write 2. Make sure you write x equals 2. Because vertical asymptotes are vertical lines, and vertical lines are always x equals a number. Okay. Horizontal asymptote. y equals 0. Yes. Okay. You have 3 cases. That's a lot to remember. Let's pretend like you don't want to remember that, right? So look at it like this. Let's pretend like. Look at it like this. 3 over x. And x is going to infinity. That's where your horizontal asymptotes are. They're out at infinity and negative infinity. So if I'm going out to infinity, yeah, it's okay. I think that's my arrowhead telling me that my water is going to be delivered tomorrow. Okay, so here we go. Oh yeah, my kids, they only drink Arrowhead. Yeah, they're very picky about their water. So, oh yeah. Okay, y-intercept. How do you find the y-intercept of a function? You let x equal 0, okay? You guys, that is like key. If you ever want to find the y-intercept of anything, any function at all, you let x equal 0, okay? So if I let x equal 0, I get negative 1.5, negative 3/2. The x-intercept, set this function equal to 0 and solve, and we get none. Okay, we're going to draw the graph. Let's find the domain right now, just because we're here. All reals except for 2. Okay, so now we're ready to graph this thing. Bless you. Now we're sketching a graph using all the information, so let's go ahead and plot everything. First of all, plot x equals 2 as a vertical asymptote. There you go. Then plot y equals 0 as a vertical asymptote. Okay. I have an x-intercept, a y-intercept of negative 1.5. So negative 1.5 is about there. And I'm ready to graph. Okay, if you know what the basic shape of these look like, you're going to be just fine. Watch. On this side, it's going to look like this. And over here, it's going to look like that. Because it starts with a parent function of y equals 1 over x, and this is all just shifting and stretching and all that from that. Now, if you're not sure, you can always take an extra point, like plug in x equals 3 into here. You plug in x equals 3, you get 3. And so you know you're going to be up there and over here. Okay? Aren't those fun? Oh, okay.
Wait, how do you know where to plot the one above the x-axis, the point?
This one?
Yeah.
Oh, I took x equals 3 and I plugged it in. So f of 3 is 3 over 3 minus 2, which is 3 over 1, which is 3.
Okay,
Yeah.
so how do we know what number to plug in for that?
I always plug in the number right next to the asymptote.
Okay.
Could you say that again, please?
Yeah, zoom out, we can't see.
Oh, no.
Oh, why didn't someone tell me? I'm sorry. Plug in 3 into the function
For the x.
Why?
to find, I wanted to see what y was equal to over here, just to get an extra point. You don't have to. Yeah, because some people were like, how'd you know it was up there? You can always plug a number in. Find it that way. Okay, let's do another one. Here we go. Vertical asymptote. Vertical asymptote. Yes. X equals 0. Okay. X equals 0. Horizontal asymptote. Y equals 2. Okay. All right. It's one of the 3 cases. But watch. You can also do this. Take the leading term over the leading term, and you'll find it that way. Okay. Just take the first, if it's in standard form, the leading term over the leading term, and you get y equals 2. The y-intercept is to let x equal 0. Uh-oh.
Can you always do that?
Mm-hmm.
Solve that way?
Yeah. Yeah. Instead of memorizing, I think that's a much better way to do it. The y-intercept would be none. If you let x equal 0, you're not allowed to let x equal 0. The x-intercept is to plug in 0 for f of x and solve this. You really don't need the bottom. It's just going to make 0. So you get what, 1/2? X-intercept is 1/2. You can write that as a point if you want to, 1/2 comma 0. Either way, or just 1/2. And then domain would be all reals except for 0. Okay, we're ready to graph. That was quick, huh? Here we go. X equals 0 is a vertical asymptote. I'm going to draw it in red this time. vertical asymptote. Y equals 2 is horizontal asymptote. Okay, so there we go. So now we have our little 4-grid thing. We're ready to graph. Let's plot a point. We have no y-intercept at all, but our x-intercept is 1/2. So I'm going to go over here and put a 1/2 right here. If I can. There we go. Now, I know what's happening on that side of the graph, okay? I know it's going like this. It's going to go through here, and it's going to go right along the asymptotes like that, okay? Now, I might not know what's happening on the left side, though. So if you want to, pick a point, any point, and plug it in. Or pick a number for x. I'm going to plug in, you want to plug in 2? 2's over here. -1. I'm going to plug in -1. Okay? So if I plug in -1, I get 2 times -1 minus 1 over -1. So what is that? 3. So I'm going to go 1, 2, 3. I'm going to put a dot right there. And I know what that's going to look like. It's going to go right along the asymptote and right along that asymptote. Done. Beautiful. Okay? So you'll find all the pieces, and then you'll plot the stuff. Ooh, the next one looks tough. Let's do it. All right, so the next one, vertical asymptote, horizontal, we're going to go through the whole thing. First thing you want to do is you want to factor, because we're trying to find the zeros of the denominator. So if we factor, we have x up top. In the denominator, we have what times what's -8 adds up to -2. -4 and +2. Okay. Do any of those things reduce with the top? No, they don't. There's no repeats from the top and bottom. So there's no holes in the graph. So these are going to be both vertical asymptotes. Okay. So our vertical asymptotes are x equals 4 and x equals -2. Perfect. All right, the horizontal asymptote. Like I said, maybe you don't want to memorize all those cases. Take the first term of the numerator over the first term of the denominator, if they're in standard form, and you end up with 1 over x. Now plug in infinity for x. What do you get? 0. So y equals 0 is your horizontal asymptote.
Wait, how'd you do that again?
Okay, so I took the top, which is x, over the bottom leading term, which is x squared. I reduced it to 1 over x, and I thought about as I'm going out to infinity or negative infinity, then it's going to be 1 over a huge number, which is 0, essentially 0. Okay? Or you can memorize. The degree of the numerator is less than the degree of the denominator, so it's going to be y equals 0. All right, the y-intercept is to let x equal 0. So you get 0 over -8, which is 0. The x-intercept is to let y equal 0 and solve, really just solve the zeros of the numerator, which is 0 also. Okay? The domain, all reals except for 4 and -2. Good. You're good at that now. Yes. Remember when you weren't?
Yes.
Is the domain always not going to equal whatever the vertical asymptotes are?
Or the holes in the graph.
Or the holes.
Yep. Whatever the zeros of the denominator are, that would be the domain. Okay, let's graph all our things. Here we go. X equals 4 is one of our vertical asymptotes. So let's draw a vertical line through 4. X equals -2 is another one. Another one. And then y equals 0 is our horizontal asymptote. And the only point I got on my graph is 0, 0. So you're going to need to plug in some points here to find out what's happening on the rest of them. So what happened was it broke it up into 3 parts. Okay? So let's go ahead and find out what's happening over here in this area. So let's plug in a number for x. Let's plug in x equals, what do you want to plug in? 5? Me too. X equals 5. Now my suggestion is to plug it into the one that you factored because it's just easier to do it that way. So plug in 5. So f of 5 would equal 5 over 5 minus 4 is 1. 5 plus 2 is 7. So I get 5/7. Really I'm concerned with is in my positive or my negative. Okay, so I get 5/7, which is, you know, pretty close to 0. And so I know that my graph is going to look like this. They always look like these branches on the outsides. Okay? It's going to go right along the asymptote and right along that asymptote. All right, go over here and plug in -3 now. Let's plug in f of -3. So I get -3 up top. -3 minus 4 is -7. And -3 plus 2 is -1. So I end up getting -3/7. Is that right? Is that what you got too? Plugged in -3, -3 up top. I'm going to check it. -7, -1, yeah. So -3/7 is down here, so my graph is going to be below the x-axis, and it's going to be like that. Okay? So I've got the outsides done. Great. Looks good. Now I got to find out what's happening on the inside. So I'm going to have to plug in another couple of points, okay? Yeah. So let's plug in f of 1, see what that's equal to. When I plug in 1, I'll get 1 over 1 minus 4 is -3. And then 1 plus 2 is +3. So I get 1 over -9, so -1/9. So that's going to be down here somewhere. Okay? And now let's plug in f of -1. So I get -1, and -1 minus 4 is -5. -1 plus 2 is +1. And so I get +1/5. So at -1, I'm up here. Okay? This is not going to be like a line or anything like that. It's going to be like a cubic function. It's going to go right along that asymptote. It's going to go through here and along that asymptote over there. Okay? That's all you need. It's just a couple of points in there to figure out what it's doing. And that would be the whole graph. There you go. They're tough, huh? Oh, it's a hard lesson. That's why I chose a block to teach it in. All right. 2 more. Last 2. Ooh, do you see letter B on this one? We finally are going to get a hole in the graph. Yes. Okay, here we go. First things first. This is really complicated looking, right? We're going to graph this thing by hand. It's really amazing things that you're doing right now. So let's go ahead and factor the numerator and factor the denominator. So difference of 2 squares, x squared minus 9. I get x plus 3 and x minus 3. And then on the bottom, I have an x minus 3 and an x plus 1. Okay. Now, before you start doing anything, canceling stuff, whatever, let's look at the domain real quick. Okay? I know it's the last question, but the domain's going to be all reals except for perfect. 3 and -1, both of them. Okay? Because they're for the original function. Now, what happens is, if I were to kind of clean this up a little bit, I would reduce those two because they're the same. Okay? So that is going to be where my hole in the graph is. So I have a hole at x equals 3. Now they're going to ask you for the hole's point, where you have to find the y value there. Now you can't plug 3 into the original, right? You'll get 0 over 0. Plug 3 into here, where you just reduced. Okay? When you plug 3 in for x into here, you get what? 6 over 4. So you get 3 over 2, or 1.5. Okay? So you get 1.5. That's where the hole is. It's at the point 3, 1.5. There's no point there. But that's how you find it. Okay? Like I said, you cannot plug 3 into the original because it's not in the domain. But once you reduce, then you can plug it in. Because you got rid of that problem that was happening. Okay, do we have any vertical asymptotes? 1? What is it? Yes, x equals -1. Okay, that's it right here. It's the 0, that it didn't go away with anything. And then what about my horizontal asymptote? Y equals, take the leading coefficient over the leading coefficient, or leading terms over leading terms. When I reduce x squared over x squared, I get 1. All right, the y-intercept is by letting x equal 0. Let x equal 0 and plug it in. And when I do that, I get -9 over -3, which is 3. find the x-intercept. The x-intercept is by letting y equal 0. Go over here to where you reduced and let this equal 0. You don't need the bottom. Do you see how you don't need the bottom for zeros? When you cross multiply, you just get 0 anyways. It doesn't matter. So that would be negative 3. Okay, we're ready. Are you ready? First of all, graph the vertical asymptote and the horizontal asymptote. Okay? So I'm going to go to x equals negative 1. There's the vertical asymptote. Y equals positive 1. And there's the horizontal asymptote. Then I'm going to graph the hole in the graph. Okay? Here's how you graph the hole. We're going to go to positive 3, 1, 2, 3, and then 1.5. So 1.5 would be right about, and draw a hole in the graph. Okay? And then I also have an x-intercept of negative 3. So this is 1, 2, 3. All right, I don't need to pick any extra points. We already know what this is going to look like. Okay? Over on this side of the graph, it's going to go right along here. And it's going to look like this. It's going to go right along the asymptote and go through that point. Okay? Up here, I'm going to go right along the asymptote. I'm going to skip over that hole in the graph and go like that. And that's what the graph should look like. Cool, huh? Wait. Y-intercept was 3. There we go. 1, 2, 3. Phew. Barely worked. That's a great problem. You will get something like this on your test next Friday. I guarantee you. Something like that. That has all the parts. It's got a couple asymptotes. It's got a hole in the graph. It's got all kinds of great things. Okay, the last part of the lesson is a little tricky. Okay. If the degree of the numerator is 1 degree greater than the degree of the denominator, then there will be no horizontal asymptote. So we knew that, right? The degree of the denominator is bigger, or numerator bigger than the denominator. It's one of our cases. We haven't seen it yet. But the graph is going to have a slant asymptote instead. So instead of a horizontal or vertical, it's going to be a slant. Isn't that crazy? Yeah. All right. How do you find that slant asymptote? I'll show you. Okay, so go ahead and we should probably factor this just to make sure there's no holes in the graph. So I'd factor out an x from the numerator and then the denominator. Nothing is going to be duplicates of top and bottom. Nothing reduces, and so we don't have any holes in the graph at all. We do have a vertical asymptote. Our vertical asymptote is at x equals negative 1. Okay, how do you find a slant asymptote? This is how you find a slant asymptote. You have to actually divide this. You have to divide x squared minus x by x plus 1. You can do that one of 2 ways. You could do long division if you wanted to. Take x plus 1 and divide it into x squared plus x. Or you could do synthetic division if you'd like to do it that way. I would too. I would take negative 1 and do synthetic division. 1, 1. I don't know if you need that 0 there or not. We'll find out. All right, so you bring down the 1. 1 times negative 1 is negative 1, 0, 0, 0. Negative 1.
The second.
Where?
It's x squared minus.
Oh, it's minus. Oh, you're right. I wrote it wrong. Thank you. Put some red on there. All right, so that's a minus. All right, so negative 1. So this is 1, negative 1, 0. There we go. Okay, let's try it again. Thank you. 1 times negative 1 is negative 1. Add, you get negative 2. 2, you get a remainder of 2. Okay. And we don't care about the remainder. It doesn't matter. What we're looking at is this right here. And this right here, if you were to write it in its polynomial form, would be what? X minus 2, right? Okay. So our slant asymptote is y equals x minus 2. It's the line x minus 2. Yeah. So we did synthetic division, and we ended up with a 1x minus 2. And so that's our slant asymptote. Okay? All right, so our y-intercept is to let x equal 0. When I let x equal 0, I get 0 over 1, which is 0. My x-intercept here is to let y equal 0. And when I do that, guess what happens? I get two answers. I get 0 and I get 1, right? 1, 0. Okay? The domain is all real numbers except for -1. We're ready to graph. Okay, let's graph the vertical asymptote first. Vertical asymptote, you go over here to x equals -1. There's your vertical asymptote. Your slant asymptote is to graph the line y equals x minus 2. Okay, so go over here to -2. That's your y-intercept. And you count slope, rise over run. You guys all know how to graph a line, right? Up 1, over 1. And so, come on. Hello, there it is. So this would be your slant asymptote. Okay. Now, I kind of ran out of room because of my mistake over here. Let me go to the eraser. Try and get rid of some of this stuff. There we go. All right, so let me continue this there and that there. Now, do you see what happened? It broke this thing up into four things again. It's just they're not straight anymore. They're really kind of weird. So let's plot all the things that we have. Okay, we have a y-intercept of 0, 0. And then we have an x-intercept of 1, 0. Right there. So what this graph is doing right there is it's coming through like this, and then it's dipping below and going back out. Right? Crazy, huh? And then over here, you can plug some points in, but they're going to be the same thing every time for these slant. It's going to be the opposite of it. So it's going to have also another one over here, like that. So it goes right along the slant asymptote and right along that vertical asymptote. Okay? And if you want to, you could graph it on your calculator to see what it looks like. They're kind of weird on your calculator. X squared minus x divided by x plus 1. See, there's 1/2 and there's the other half. Yeah? Right here? The 2 x-intercepts came because when you set this numerator equal to 0, like when you set y equal to 0, you're essentially solving this. And what are the zeros of this? You get 0 from there and 1 from there. It's like you're solving a quadratic. It's already been factored because we factored it. Yeah, so that's where they came from. And then when you do that, you get 2 of them, so it dips below and goes back out. Yeah. Now, I have good news for you. This. That's really cute. The slant asymptote is really, no, I try not to really focus on that. I want to focus on the other ones more. This might be more of a bonus question on a test, okay? So, yeah, and it's not that bad. But, I mean, the other stuff's still hard, so this is like a little extra hard. I think in RAM they don't even cover slant asymptotes because it's too hard.